Oui, bonjour. Donc, moi, c'est Julien DRUET du Cerema.
Hello, Julien from the Cerema in Nancy, and I'm going to be talking to you about a project concerning the surface layers. This is a project that we entered into concerning the residual lifetime of the road pavements. The project is divided up into two sub-projects. First of all, the aim was to develop a tool and a methodology to enable objective assessment of the surface conditions of the site studied. And secondly, we wanted to evaluate the surface life of the surface courses using recycling techniques, notably using warm asphalt, for example. So for the first sub-project, the work that we needed to do was make a list of the relevant sites. A lot of work was done at this stage because we knew that it's one thing to have the sites, but then you've got to find the sites, find the documentation that goes with them. A lot of these sites had been set in place over 5 years ago, and the ideal thing is to have sites that are more than eight years old. And of course, we wanted to have at least 30% of the sites that had gone through a recycling process, recycling on the surface course using a warm type technique. In the end, 51 sites were identified, 37 using warm techniques. The average age of the sites was 2008 and the maximum age 2015. So what kind of tool did we use? Well, we decided to use the latest technologies in terms of surface monitoring. So we used the LCMS sensors, and we also have the Aigle 3D. I'm not going to go into detail on everything we did in terms of the 3D measurement because we talked about this testing method this morning. Obviously, what we want is a 3D model of the road pavement, and then we want to be able to produce the descriptors. What are we most interested in? Well, those that talk about the surface deformations, the cracking, stripping, cracking, etc. And we wanted to push to one side all of the descriptors of deformations that are basically more structural. In other words, the short waves, long waves, those we were less interested in. The difficulty of working with this method is as follows. Up until now, we've tended to use our systems for analysing the national road pavement network, and we're used to analysing 25,000 kilometres of network, whereas all of a sudden here we were asked to produce an operation that was a lot more detailed, just covering a few hundred meters. So it's not the same work, not the same job at all. So we had to work out exactly what methodology we were going to apply. We were able to practice on a test site. It's called the RD681 at the level of Autun in the Saône and Loire département of France, because with this portion of the road, we had lots of data, lots of information. The operator was available to help us. We had plenty of geological data as well. So I repeat, that way we were able to perform a test on this section with different types of courses as well. This is just to give you an idea of the results that we were able to achieve. As we said this morning, you can see all of the different forms of deterioration. You can map it out very much in standard practice. That's what we've been used to doing up until now. In this example, you can see the cracks, the rutting, the raveling, and also the areas with no damage. Those are the areas that we evaluate, that we assess, and then we separate them from those areas with rutting and with cracks. Within the scope of the project, we exploit this kind of data for the whole area, and then we produced ratios for the whole area and graphs and averages, minimum, maximum values, and all of these will be a lot more legible than this kind of portrait that is painted just using the surface area. In the end, we came up with 4 different sites, mainly with a specific asphalt mix, BBSG, I think he said in French. This is a kind of asphalt that is used throughout France on many different roads, but not on all of the sections. And then we had another section that we hadn't thought of initially speaking that was very interesting. This was part of the RN4 in the eastern part of France. That is a part that was added at a later date. Let me now show you in a bit more detail the results that we obtained for the different sites. The first site was a section just north of Dijon, around 2 kilometers. This is a section that was quite a fun section because it's pretty much in a straight line. When you've got bends, of course, you can come up against other issues on the road pavement. So here the structure was very good, pretty homogeneous. A bit further down the line, I'll talk about the project. We look at the surface in this study, but the damage to the surface can lead to structural damage. And of course, we've got to put things into context, and that's sometimes rather difficult. So for this portion, let's say that the road traffic was pretty standard, a certain number of heavy-duty vehicles per day. We had about 10% of aggregate asphalt mix. You've got the different types. The third one, for example, had a specific Agimac surface. And then we also had other portions that were older portions of the road that dated back to 2011. And so the materials were approximately 10 years old. Once we analysed all of the data, the first thing we did when we looked at the data was see that, wow, visually speaking, it was very interesting because you can see the clear dividing line. You can see the cracks. On the left-hand side, you have the older portion of the road, so that's why there's a lot more cracking. Sorry, it's on the right-hand side, on our right-hand side, so that is quite evocative. Next, when we looked in relation to the results, we'd seen the start of the section, and then you can see that there's a slight change. So we went back out into the field. We worked with the managers, the people who managed the venue, and they took a look and they said, "Ah, yes, there's no doubt." With the GPS coordinates, we were able to align the different sections, and we realized that we'd made a mistake. Initially speaking, in the report, we'd put the sections in the wrong order. Sometimes until you go and look in the field, you can't necessarily get it right. But very fortunately, we were able to go back and check and then put them back in the right order. We did this actually for all of the documents that we had for all of the sections of the road. Once we knew that we'd put them all in the right order, as I said earlier on, in terms of the surface information, we summarized it for each document that we had, so for each portion of the road pavement. Here, you've got the information for one of the portions, and what you need to look at in particular is not necessarily the minimums and the maximums. You should look at the averages, because sometimes you can have slight drifts in terms of the measurements. But if you look at this, we can see that for the rutting, the ruts are very low level, about 2 millimeters on average. You have a bit more for the older sections of the route. That's totally normal as well. But the rutting, for example, was not particularly bad. After that, we looked at the macro texture. And here, once again, we were able to observe pretty much the same thing. You can see that on the extreme left and right end, there's a bit higher impact, but not as much as all of that. And for all the other sections, the values are pretty similar. The average MTV values are reasonable. And it doesn't look as though it's very discriminative in the context of this study. Afterwards, what we saw visually can be confirmed in the tests that we performed. In other words, when it comes to cracking, there's a big difference between the older sections and the more recent sections. We numbered them. The older sections have more cracks, but also we can see differences between the different sections depending on how recent they are. For example, there is more significant cracking on the asphalt mixes with 40% wrap aggregate compared with those with only 10% wrap aggregate. The cracking densities, nevertheless, are relatively low. We were able to note that it was barely visible. This was the case for all the sections installed in 2011. So we were able to say that the surface still had another 10 years in it. We can see also that there's no clear difference between the Regifalt and the Regimac. There was a question of the additive. We can talk about that on the section slightly further down the line. Another point that is important is the density of the cracking. With the 3D methodology, we're able to see occasional cracking on the surface. And so for the surface data, we have a buffer approach. And within the scope of this project, we talked about 10 centimeters. I'm sure you're able to understand that if we have a buffer of 10 centimeters in a very random manner, we're going to double potentially the amount of cracking that we see. So what you need to do is compare the cracking, intrinsically speaking, compare all of the cracking data with the other elements. Next, I'd like to talk briefly about site number 2. This was a stretch of departmental road. Here we had 4 sections, one with 20% of wrap aggregate, one with 40% of wrap aggregate. You can see that there are differences in terms of the cracking. There's more cracking here with the 40%, a lot more than with the 20% of wrap aggregate. Nevertheless, if you look at the cracking, it's pretty superficial. So the crack density, I repeat, is relatively low. But these results are interesting because of the differences between the different percentages of wrap aggregate. Let's now move on to sites 3 and 4. We don't have any sections without recycling. And on site number 4, or rather site number 5, is the last site that we were able to work on. This was the national network. The rest was part of what we call the departmental network. Here you get a lot of traffic. And one specific feature of these portions of the road pavement is that you have 2 sections of warm asphalt, 2 hot asphalt. Here clearly we can see that there is more significant cracking on the warm mix asphalts, that's sections 1 and 2, than on the hot mix asphalts, that's sections 3 and 4. The warm is a bit more cracked than the hot, nevertheless. And the recycling is a bit more cracked than the non-recycled, but there's not that much of a difference. You do have to be careful, nevertheless, because statistically speaking, the standard deviation is very, very low, extremely low. And the second thing is that on these sites, we do have big structural problems. We have certain bumps that appear on the road that have been redug by the management authority. These kinds of phenomenon, we're not used to dealing with them, and they can have an impact on the topography of the site, and we're not necessarily that good at measuring them. So these sections, well, one of the sections was in an upward slope, was in the lower part of the slope, and this is where I believe there's the most likelihood for there to be a bit of vegetation and water, stagnant water, and that's why there are a certain number of structural differences, I believe. I removed everything I could, all of the transversal cracks, but there might be a few structural cracks due to the vegetation, as I said, and due to the water that stagnates in this area. Next, this is everything that we did in relation to the 3D equipment, and we thought it might be interesting to perform an analysis on the equipment to perform the characterization of the different materials, particularly for the asphalt mix, to see how it ages, to see whether we could perform any comparisons. So we performed a certain number of tests, the standard tests that I'm sure you're familiar with. They are called the penetrability tests and then the average RBSP test. We decided to perform the tests in the Vendée region, and we took into account some of the sections as well that we saw earlier. We can see that the penetrability is a bit higher for certain types of aggregate than for others. That's logical because they're not quite as hard as some of them. Nevertheless, you can see that the results vary, but there's not much of a difference at all, because in fact we're talking about the same class, exactly the same class of aggregate. Next, I just wanted to talk about the university tests that were carried out in the laboratory. This is what we call sequential stripping. The aim of this test was to dissolve the bitumen of an asphalt mix in sequence and then establish the extent to which it oxidates and then look at the solution that you can recover. The solution was recovered, and then we performed an infrared test on the solution that we'd recovered. And this simply enables us to see what the aging process looks like in terms of this layer. You either work out whether the mix is homogeneous or whether it's begun to separate. Here you've got the main results that we obtained following on from the measurements. Obviously, we look at the slope. That's very important. If the slope amounts to 0, then it means that the results should be homogeneous. This was the case for pretty much for all the samples. And as you can see, the BR is very close to 1. So overall, the results are pretty harmonious. The conclusions of the tests are here on the screen. In all 3 cases, the binder remobilization is satisfactory. Even if it's a bit more homogeneous with the 20% mix than the 40% mix and with the regenerator and the 40% mix without the regenerator, but pretty much not much difference at all. Very few differences in terms of the aging of the asphalt mix.
Here's a summary of what we did in most of the sites. It's not very visible here, but what's important, this is included. It allows us to have a little bit of everything in one graphic representation, knowing that you can't really compare the sites between them because of different climate conditions and different soil. And so the conclusions, the outlook is what I was saying. After a few years, about 10 years, we see that asphalt mixes with high RAP aggregate have a higher level of cracking than those with no RAP aggregate. And despite everything, after 8 years of service, we see that the surface courses do play their role. The sequential stripping test showed that there's good overall binder remobilization and penetrability and softening points. There isn't much difference between the various bituminous or asphalt coverings. For the findings and outlook, perhaps, for the critical analysis of all this, let's say, I put some of the points where we have to continue monitoring and the choice of the processing tools. The buffer has a great influence. We don't necessarily make distinction between transversal and longitudinal cracks, even if it does. I drew them, and I didn't take over. We did take into account the severity, which may be also another source of analysis. So the idea would be in the future to look at the length of the cracks and the width. We should be able to do that with the tools we have. And like I was saying, the size of the samples, we have 5 sites. There are only 3 that can be used. So doing an analysis of 3 sites, we need more sampling. That could be affect the results, which are quite interesting. And then, as I was saying, there's what's difficult to understand is the influence of all the parameters that can be available on the aging of the surface, which aren't obvious. It can be how it was applied, how it was manufactured, climatic conditions, the traffic, there's the nature of the soil, also drainage. There are many, many parameters, and that you have to be aware of that we can't always be exhaustive. And the last thing is, because of the conclusions we've made, is to try, ideally, is to have a complete analysis of the complete life cycle of a road. If I put recycled products, I might lose some of the life cycle, but I'll have a better impact environmentally. So for the entire road, what's the best arbitration? The idea is to quantify, which I've never done, what is the benefit in the final analysis. And I think that's it. Thank you.